today's classes. Hello and welcome to today's class. So we're looking at chapter 2.2 of our learning guide. We're on page 53 and the topic is functions and relations. So we'll start with a definition of what a relation is. And we'll be like relation okay, I want you to write like I'm writing on my hand. So a relation is a rule which associates each element of one set with at least one element of another set. Okay. A relation is a rule and it associates an element of a set with another element of another set. At least one element of a different set. And a function, it's also a rule. It's also a rule that associates elements of one set with elements of another set. So judging by these definitions, Joy, would you say there's a difference between a relation and a function?
No.
Why do you say no?
Because they're all associated with two sets.
You don't what? Because we don't what?
I was saying they're all associated. They work as sets. Set A works with set B, so on and so on. So
Okay.
there's not much of a difference. Like similar.
Okay. So I think the relation is part of a function.
Yeah.
So for example, if we think of y equals x plus 1 as a function, there's several values of the set x that map onto certain values of y, and they map alongside the line or curve of the function. But a relation is just a rule between an element of a set. So it will be an x value of -1 maps onto a y value of 0. That's the relation. And the function would be the unique association of x values to the y values for a specific like in a curve or line or whatever. So relation would be a rule that associates an element of a set. So it would be one x value maps to one y value. But a function would be the function y equals mx plus c maps x values to y values, and on that y equals mx plus c, if x is this much, then y is that much. That would be one relation, but the function would be all the other points. Uniquely another set. So yeah, Functions can be one-to-one relations or many-to-one relations. One-to-one or many-to-one. What do you think that means? One-to-one.
Well, the graph can only, the line can only cut the axis only once.
That sounds like a definition for y-intercept.
A one-to-one is that for one point you only have one corresponding, for one x value you only have one y corresponding value.
Okay, that makes sense. And then what do you think it means if a function is many-to-one relations?
We can have many x values that have only one corresponding y value.
Okay. You think you can think of an example like that?
The smiley one, it's a hyperbola.
Parabola.
A parabola. So a parabola is an example of a many-to-one. Because you have two values of x and then you have one y value.
Okay. So this would be maybe a straight line and this would be maybe a parabola. Because you've got two x values that map onto one. That makes sense. That does make sense. Yeah, because for parabola of y equals x squared, at x equals -1, y is 1, and at x equals +1, y is also 1. So we do have many x values mapping to one y value. So that is an example of many-to-one. But there's other types there's other constructions in maths rather that are not necessarily functions. For example, if you consider the relation x squared plus y squared equals 4, the relation describes a circle of radius 2 centered at the origin, which is the coordinate point 0, 0. And if we let x equal 0, y squared is 4 and y is either positive or -2. So something like, okay, maybe my origin is not exactly at the center. Also not exactly at the center. Okay, that looks more or less like it. 2, -2, -2, 2, xy. Alright, so if this is x squared plus y squared equals 4, when we let x equal 0, y is either positive or -2. And then the same, I guess, holds for where y is 0, x is positive or -2. But this is a one-to-many relation because a single x value relates to two different y values. So this would be one to many. This would be one to many. Okay. Given the graph of a relation, there's a simple test whether the relation is a function. It's called a vertical line test. If it is possible to draw any vertical line, a line that is a constant x which crosses the graph of the relation more than once, then that relation is not a function. So again, with our very circle, if we have a vertical line crossing at, if we have a vertical line, have a vertical line crossing somewhere at x is -1. Then that line crosses the circle or the construction at 2 points. That vertical line crosses the construction at 2 points. And because of that, we can say that that is not a function. But if we have a parabolic curve and our curve looks something like that, we don't know really, we'll just call it y equals a x squared plus bx plus c. If we do the same thing and the vertical line crosses maybe somewhere there, then it only crosses this once. I guess you could say the same with a straight line, because then it will cross it maybe once. Right. So in that case where the vertical line crosses the construction once, then if it crosses the construction once, that is a function. Vertical line must cross construction once. Any more than that, it's not a function. Not a function. So this applies when you have an illustration of a graph, or you're given points to plot and they map out some kind of graph or construction. And then using the vertical line test, we'll be able to test if it's a function or not. Trying to sit like you. Yeah. So let's quickly do exercise 2.2 to see whether or not the functions that are given are, the graphs that are given are functions or not. So I'll just make the exercise 2.2 on page 55. Page 55. So we've got number 1a, which is something that looks like an upside down or frowning parabola. B is something that looks like a straight line, so say that's x, that's y, and the straight line runs like that. C would be something that looks like a wave. So that's x, that's y. Maybe I should do these with different colors so that we can see which ones are the axes and which ones are the functions. Okay. Then D is like this. Ooh, I like D already because it's gonna have us challenge whatever it is that we're thinking so far based on what we know. E on E. So E, that's X, that's Y, X. E looks something like it's a piecewise function. Do you know what a piecewise function is?
No.
So it's a function that's like piece. Yeah, so there's different pieces to it. It's one function, but it's got different components. So these are like on 1 point. These are also on 1 point. F is a circle of origin. Alright. X, Y, G. It's half a circle.
It's a semicircle.
Oh yeah. Semicircle. Okay, I tried, guys. I tried. Freehand drawings are not so easy to just draw off the bat like that. Remember, our test is a vertical line test, right? X, and this curve is the inverse of a parabolic curve. We're going to use the color orange to run our vertical line test. Okay, starting with A, which is a frowning parabola. If you draw a vertical line, it's a function. Okay. So just put orange tick, function. And then B,
It's also a function.
it's also a function. C, also a function. Great. D, you don't know.
Yeah, it'll pass the horizontal test. It'll pass the horizontal test. At this one, I'm not sure because it's just going right over it.
Just going right over it, right? Let's visit the rule again. If more than one intersection point exists, then the intersection corresponds to multiple values. X value. So there isn't a clear definition about if the vertical line does not even intersect the line, the curve, whatever, or if it does. Let's say the vertical line runs over the vertical line of the graph.
It's not cutting, it's running over it.
Okay, fine. Let's go on the other definition of the other explanation of the concept, which says one to many, where one x value maps onto many y values is not a function. If we have a straight line that goes vertically like that, it's one x value, correct? But how many y values do we have? 2. Oh, more than 2, because you've got a y value there, one there, you've got one in between those 2 points. So there's always a y value for that one x value. So it's many to it's 1 to many. Yeah. So because it's one x value to many y values, it's not a function. So that definition suffices. Not a function. Okay, let's look at our piecewise function. There's one piece, another piece, one piece, another piece, another piece. If we do a vertical line test,
pass.
Yeah, pass. So it is a function.
Yeah.
It's just not continuous. Yeah. This one is definitely not a function. What about the semicircle?
Semicircle, it is a function.
It's a function, right? And this one?
No, it's not a function.
It's not a function.
But it will pass the horizontal test. Yes.
Not a function. Alright. You can practice number 2, etc. You just have to plot them, and then after plotting them, you'll find what they look like. And then, yeah. So I want us to rush to the other one, which is function notation. Alright. For the function y equals f of x, y is the dependent variable because the value of y, which is an output, depends on the value of y. So given y equals f of x, y is dependent.
On the value of x.
Yes, and x is independent. This implies that we need an x value to have a y value. That's the long and short of it.
Yeah.
Alright. Similarly, if g of t is two t plus 1, then t is the independent variable and g is the function name. So whatever, if it's y or if it's s, doesn't matter. That would be the dependent variable. So if h of x is 3x plus minus 5, and we need to determine h of x equals 3, then 3 is 3x minus 5. Then if we add positive 5 on both sides, we get 8 equals 3x, and x is 8 over 3. And if h of x is 3x minus 5, and we need to determine the value of h of 3, then we find so to determine the value of h of 3, then we find the value of h where x is 3. So h of 3 would be 3 times 3 minus 5, which is 9 minus 5, which is 4. Then we have inverse functions. By the way, up to so far, this is like grades 8, 9, 10, and 11 for the most part. So if we are to find inverse functions, so I like to use the analogy that an inverse is like a reflection. Because when you look at yourself in the mirror and you raise your right hand, the mirror reflection raises its left hand. Not always.
No.
What kind of mirrors have you been playing with?
My mirror, when I raise my right hand, it shows me my right hand.
No. The reflection's hand is the left hand. No, because when you are facing the mirror, you are yourself.
Yeah.
But the light rays from you being reflected into the mirror are inverted.
Only when I'm facing that way.
If you're facing the mirror.
I'm facing the mirror.
Yeah.
Right. When I raise my my right hand is going to show.
The reflection illustrates the inverse.
Yeah.
So your right hand is showing, your right hand is being reflected, but the reflection raises its left hand. Not you. Your right hand is up, but the reflection's hand is the left hand.
Okay.
Yes, so I like to use that analogy. That's because, okay, but anyway, when we look at these functions, it kind of works like that. There's always a point or an axis about which that function gets mirrored. And because it gets mirrored, then that's where you get the inverse function, which is denoted f, I guess, to the -1, to just illustrate that it's inverted. Sorry, I have to get the charger. This thing is going flat. We must have power for it. Alright, so y equals f of x indicates a function, and y sub 1 equals f of x sub 1. This means that we must substitute a specific value of x sub 1 to get a corresponding y value, right? Then in the same way, f inverse equals y, rather f inverse of y equals x is the function, and likewise f inverse of y1, or certain value of y, indicates that we must substitute y equals y1 to get x equals x1. And then a function must be one-to-one, must have one-to-one relations if its inverse is to be a function. So this is an important condition for an inverse function to be a function. Its original function must be a one-to-one relationship, must have a one-to-one relation. I just used original for lack of right. So now we look at, I guess, a discussion of the method, and we're told that given f of x, we determine f inverse of x by interchanging or swapping x and y in the equation, making y subject of formula and expressing the new equation in function notation. So it's a three-step process. Okay, so if an inverse is not a function, then it cannot be written in function notation. For example, let me do this big solid exclamation mark. If if inverse function is not a function, inverse is not a function, then it can't be written in function notation. For example, if we have the function f of x equals 3x squared, it can't be written as f inverse of x equals plus or minus a third x square root of a third x, because it's not a function. No, wait. The inverse cannot be written as that, as it is not a function. Okay. The English there is confusing. Therefore, we write y equals plus positive or negative square root of a third x, and conclude that f is not invertible. Alright. If we represent the function f and the inverse function f inverse graphically, the two graphs are reflected about the line y equals x, sorry. So this is the mirror thing I was talking about, where if we have a function, let's say it's an exponential function, this is x, then somewhere we have a line that equates to y equals x, which is like our mirror boundary, and that function is inverted along I guess you could say that y equals x line. So green curve would be f and orange curve would be f inverse. Right? Any point on the line y equals x has x and y coordinates of the same numerical value. For example, if this point here is 1, x equals 1, and this point there is y equals 1, then there's a point where they meet up, and that point is 1, 1, which just illustrates that the coordinates have the same numerical value. So the line y equals x, which makes sense because for every x equals this, then y equals the same. Alright. Yeah, so it's exponential graph. The green is the function, and then the orange is the inverse. Alright. Another important thing, our f inverse is not an exponent, It's just to indicate the case of an inverse function. So we shouldn't confuse that with exponents. And secondly, we shouldn't confuse the inverse of a function with the reciprocal of a function. Do you know what a reciprocal means?
No.
So,
I know the word.
eh?
I know the word, just don't know the exact definition of it.
Okay. What does the word reciprocal mean?
Repetition, something like that.
Something
Something in those lines.
To reciprocate means, let's say we have a ball between us, and I throw it to you, and you catch it, and then you do the same. You've just reciprocated my action. Ball in your hand, you throw it to the person in front of you. Yeah, so that's reciprocal. So okay. So just to illustrate the difference between inverse and reciprocal. Alright, so we'll have f inverse of x, and the reciprocal would be f of x all to the power -1. And in the case of that, then that entire function, we apply the rule of exponents, which is 1 over f of x. Alright, that's the one thing. The second thing is f of x and f inverse of x are symmetrical about the line have symmetry about the line y equals x. And as for reciprocal, if we take f of x and we multiply it with its reciprocal 1 over f of x, the net result is 1. Which makes sense, because even if you had ax squared plus bx plus c over there and ax squared plus bx plus c, that would divide with the other one, and then we still get an answer of 1. So these two conditions clearly illustrate that the two are incomparable. Just do that.
This reminds me of the gradient of a perpendicular.
Yeah, something like that. It's almost like that, yeah. Although that's a different concept entirely. But they work similarly. Yeah. So if we look at an example, g of x would be, let's say it's 5x, then g inverse of x would be x over 5. And that is because if we follow the 3 rules, remember we have to interchange x and y in the equation. So if g of x is 5x, y equals 5x, then we start by interchanging the 2. So x equals 5y, right? And then after we do that,
we have to return them back to
thing, yeah. So 1. So our steps here, interchange. And then step 2, you said is what? You said step 2 is 2? You just mentioned it now.
Or like we have to reverse it back to its normal, to a function notation.
Or before that, what do we have to do?
Before that?
Yeah, because I get we've written it as we've swapped the x and y unknowns. And then what do we do next?
Making y the
subject of formula, yeah. So y is subject. So then y would be x over 5. And then the third step is what?
How do we do function notation?
Function notation. That'd be f of -1 of x equals x over 5. Oh, my bad. It's supposed to be g. G for Jesus. You don't remember that one?
No.
For Jesus. Okay. However, with regard to this one here, if g of x is 5x, then the reciprocal is 1 over g of x, which is 1 over 5x. So far, so good. Alright. So we're gonna do the inverse of a straight line. Inverse of y equals mx plus c, or y equals ax plus q. Q for cute. Determine the inverse function, the inverse of the function rather. Word example 4, which is on page 58. This would be p of x. Oh yeah, find a function that starts with p equals minus 3x plus 1. And then we must plot p of x and p inverse of x on the same system of axes. System of axes, yeah. So what's our first step?
Is swap x and y.
Swap them so long. So y equals minus 3x plus 1. If we swap them, then we have x equals
minus 3y.
Plus 1. Awesome. And then the second step is to
Make y the
subject of formula. Great. Then such that if x is minus 3y plus 1, we minus 1 on both sides, so that x minus 1 is negative 3y, and divide by negative 3 on both sides, so that x over negative 3 plus 1 over 3 equals y. And then we now give it inverse notation. Then this becomes y, or rather p inverse of x is negative x over 3 plus 1 over 3. That's clear. Sorry. Now we must plot these two. Let's plot them simplistically. So let's do x, p of x, and p inverse of x. So we have minus 3, minus 2, minus 1, 0, 1, 2, and 3. Okay, so for our first learning for our original function, when I noticed I wrote x somewhere I shouldn't have.
Okay.
Yeah. So for p of x, which is negative 3x plus y, when x is negative 3, or y is 10, when it's negative 2, 7, negative 1, 4, 0, 1, negative 2. So if the difference is 3, 3, 3, that should be negative 5, that should be negative 8. Alright. Then for the inverse, y equals negative x over 3 plus 1 over 3.
Negative 2 over 3.
Negative 2 over 3. Okay. When x is negative 2?
Negative 1 over 3.
Negative 1 over 3. Great. And when x is negative 1? 0. Okay, good.
1 over 3.
1 over 3. X is 2?
2 over 3. 2.
2 over 3.
When x is 1, it's 2 over 3.
When x is 1, it's 2 over 3. Okay, cool. And when x is 2?
You skip 0. When x is 1, it's 2 over 3. 1.
Okay. So it's 2 over 3. And when x is 0?
1 over 3.
1 over 3. Okay, so I'd written it correctly. Okay, cool. Then when x is 2? 1. Okay. And when 4 over 3. So check. Wait. Is this how the coordinates are supposed to look? When x is negative 3, our answer is 2/3. When x is negative 2, our answer is a third. When x is negative 1, y is 0. Wait.
You know which one I used? I used this one.
Yeah. So
now I'm using the other one before. Now I'm using this one.
The negative 1 over 3 times x minus 1. Oh, you're using that now?
Yeah, and then it's giving me 4 over 3.
For the last one? For x equals 3.
Negative 3. It's giving me 4 over 3.
It's giving you 4 over 3.
Yes.
Okay. Positive.
Yeah, position 4 over 3.
Okay.
And then it gives me 1.
For the second one.
2, yes. And then 2 over 3.
Then 2 over 3.
No, for negative 1.
For negative 1.
Yeah.
Just 2 over 3.
2 over 3.
Okay. And for 0, it's 1 over 3.
Yes.
For 1,
It's 0.
0.
Because 1 minus 1 is 0. 0 multiplied by negative 1 over 3 is 0.
Okay. And then when x is 2,
Negative 1 over 3.
negative 1 over 3. And when x is 3,
Negative 2 over 3.
negative 2 over 3.
It just reversed everything. It reversed everything.
It reversed everything.
Yeah. Because this was this way. And this time
Unless we weren't adding the signs correctly.
Like,
we probably were not doing the signs correctly.
I think I forgot the negative on that equation.
Is it?
I think so.
Let's check.
I wasn't.
You weren't using the negative.
Yeah, I forgot the negative.
Okay.
Yeah.
Alright. So that probably means you could lose a lot of marks if you don't get the signs right, because then the graph is going to be all wrong.
Yeah.
I hope that's straight enough. Straight as an arrow. We're gonna plot the line y equals x. Okay, I think that's y equals x enough. Okay, so now we'll have that's x, that's y, negative 1, negative 2, negative 3, 1, 2, 3. Alright. So for p of x, which is our original straight line, at x is negative 3, y is positive 10. Okay. So we have 10 all the way to 8. So I'll just do this. 5, 10. And then we'll do this. Negative, negative 5. Negative 10. Alright. So where x is negative 3, y is positive 10. So we'll use the green line to plot that. In negative 3, we've got positive 10. At negative 2, we've got positive 7. So 5, 6, 7, somewhere there. Just do that. Positive 7 is somewhere there. At negative 1, it maps to like a 4, so somewhere there. At 0, we have y-intercept at 1, so it's a bit higher, but just this is probably supposed to go lower. Just make 7 a bit closer to 5 there, so that we can have 1 a little bit off there. 0, 1. At 1, y is negative 2, so maybe somewhere there. At 2, y is negative 5, so somewhere there. And at 3, y is negative 8, somewhere there. Somewhere there. And when we plot, it's gonna look a little bit like a snake, because it's not drawn to scale, but at least it gives us an idea. So that's p of x. And then to plot the other one, at negative 3, we've got 1 and 1/3. So if there's a 1, 2, 3, 4, 1, 2, 3, 4, So 1 1/3 is just above. Okay. Just above 1. So somewhere there. That's -3 is to 4 over 3. Then the next one at -2, we've got 1 exactly. At -1, we've got 2/3. So somewhere there. At x equals 0, we've got 1/3. Then at x is 1, we've got 0. At x is 2, we've got -1/3. So somewhere there. And at x is 3, we've got -2/3. So just below 1, somewhere there. And this line is gonna be, I'll just do this, -2 is to 1. -1 is to 2/3. 0 is to 1/3. 1 is to -1/3. 2 is to, no, that's supposed to be 0 there. Why is on TV? Why you don't stop me when I'm writing -1/3 instead of 0? -1/3, and this here is 3 is to -2/3. Alright, so we can, I hope it's straight-ish. Something like that. Oof. A little bit off, and off that y equals x mark, but that's because it's not to scale. But this would be more or less the procedure to follow when plotting these graphs, and that line should actually cross there. But yeah, thanks to my data ring hands, yes. Again, to determine the inverse of a function, we interchange x and y. We make y the subject of the equation, and then we write it in inverse. Yeah. Therefore, if a linear function is invertible, its inverse will also be linear. Before that, if y equals ax plus q, then y inverse is 1 over a times x minus q over a. Minus q over a. And if linear function is invertible, then its inverse will also be linear. So that just means if we can find the inverse of a linear function, then its inverse is also a linear function. Alright. I'm gonna skip worked example 5 because it's the same as the one we just did. But it's got some important things here. It's got some important things here. Okay. Let's go back to this graph here. Yeah. If we are to determine the significant characteristics of the graphs, what are we going to determine?
Intercepts.
X and y intercepts, good. And what else? Domain and range.
And then when you have 4x, do we have axis of symmetry there?
Nah, in a straight line, nah. It's not
And we
necessary.
also have, we don't have turning points, so I think that's all.
That's it. So significant characteristics would be x and y intercepts and domain and range.
Yes.
Let's quickly find those ones for these two. So for the green graph, x-intercept would be where y is 0, where y is 0, x would be a third, 1/3, and where x is 0, and where x is 0, what is that? Where x is 0, y is 1. Okay. And the domain would be a set of x values such that x is an element of real numbers, and the range would also be a set of y values such that x is an element of real numbers. Can we say the same or similar? Can we do similar for the orange graph?
Yes.
Okay, so x-intercept would be where y is 0, which is where that is 0, x over 3 equals 1/3, x is 1, and y-intercept is where x is 0, so where x is 0, y is a third. Okay, and domain would be a set of x values such that x is an element of real numbers, and the range would be set of y values such that y is an element of real numbers. Alright. Another important thing when we are dealing with these inverses, it's important to note that a can never be equal to 0. Why do you think that's important?
Because A is the gradient.
Yes, it is a gradient, but if it equals 0, what would happen to the inverse function?
It also equals 0.
Not really. If you think about it in terms of the a being the denominator in these fractions a, what will happen to the function if we have a equals 0?
It would be an error.
Yeah, it would be undefined. So that's why a cannot be equal 0. Yeah. Then I'm gonna pause a little for with the homeworks. I wanna make sure I catch up with everything. Yeah. Then let's do a quick 5-minute recess. I just wanna go stretch out my legs for like 5 minutes and then I'll be back. now do inverse quadratic functions. If my mood is a bit offish, I don't know what's up, but I think my energy levels are not as nice as I like them to be.
It's okay.
So quadratic functions. Yeah, so these are functions of the form ax squared, remember that? And the inverse of one like that, if we look at word example number 6, we have h of x equals 3x squared. Remember our first step is to interchange, right? So y equals 3x squared, so we'll have x equals 3y squared. Alright? Then we make y the subject of the formula. Okay? So x is divided by 3 equals y squared. And then we take the square root, so y becomes positive or negative square root of x over 3. Just make notes on the side. Swap x and y to y is subject of formula, and here we divide by 3, and here we take the square root on both sides. Alright. It's important that x is also greater than or equal to 0. You must always put that. That is because it tells us we are aware that if x equals 0, if x is negative, we will have a negative square root, which we don't, it's undefined. Yeah. The square root of a number is always a positive number. Yeah. Right, so we can plot this x, h of x, h inverse of x. Just a simple plot. -3, -2, -1, 0, 1, 2, and 3. Right, so it's 3x squared, right? When x is -3, what's y for h of x? No, wait. First for
the normal
function, yes. Y equals 3x squared. 27. Okay. So then that's 4 times 3, 12. 3, 0, 3, 12, 27.
I'm still on 3.
Okay.
3, 12. Yeah, I think it's many to 1.
Many to 1, yes. So, okay, if we have for the second one, if x is -3, -2, or -1, we don't have values for that. So we can skip this part here. It's out. But now what happens when x is 0? Our thing is 0. Ne? Now what happens when x is 1? Square root.
It's a root of 3 over 3.
Root 3 over 3. Okay. And then what happens It's positive or negative, remember?
Positive.
Remember, it's
plus minus root
plus minus root 3 over 3, yeah. And
plus
when it's 2?
Root 6 over 3.
Root 6 over 3, okay. And then the third case?
1.
Just 1.
Yeah, just 1.
Alright.
And then for plus minus root 6 over 3, it's 0, 0.81, 0, 0.82.
2, okay.
Okay, for the first one is negative, it's 1 over 3, right?
It's root 3 over 3.
Root 3 over 3.
Yeah.
It's 0, 0.58.
58. Okay, great. Oof. I think we should shorten it maybe to between negative 2 and 2, because that would be easier to work with and to plot. Okay, I just need to make that a little bit longer there. Hopefully this time we get the correct line y equals x. Our first graph at x is 0, we have 0. At x is, let's say, 1, 2, 3. Negative 1, negative 2, negative 3. Okay, so for 1, let's say we have 3 there. 1, 2, 3. 1, negative 1, negative 2, and negative 3. Alright, so start with green, which is y equals x squared. So at x equals 1, we've got 3. And at x equals negative 1, we've also got 3. So we can safely say our curve does something like this. Turns there. Dish. Medium. Right? And this is h of x equals 3x squared. Right. And then orange. Right. So we add 0, 0. Our graph can never be on the negative x-axis. For x is 1, we've got 0.58. So where x is 1, we've got y equals, if that's a half there, so 0.58 will be somewhere there. So we can plot nyana somewhere there and plot something nyana somewhere there. Then my nose is full of moisture. It's full of sweat. The other one is 0.82 for 2. So at x is 2, the thing is closer to 1, so it maps somewhere there, and it maps also somewhere there. And where x is 3, it maps strictly onto 1 and also onto negative 1. Therefore our curve looks something turning point. Almost had it, but almost does not count. Ampor marnis tampor. Do you know that saying?
Yeah, ampor marnis.
Marnis tampor. Yeah.
But I couldn't do it.
Okay, this one almost went through the line y equals x, né?
Almost.
Almost, but that doesn't count because, yeah.
But it's the same thing, babe. If you look closely, it's similar.
It's kind of similar, yes. But everybody knows.
But the why this line didn't cross directly in the middle.
Yes, that's my point.
That's sad.
H inverse of x is plus minus x
It's
over
your
2.
line that's the problem.
Aye, that line looks more straight and the curve looks more curved.
It's the line that's the issue.
Let's quickly do a vertical line test on the inverse.
No.
Is it a function?
No.
It is not. It is not. It is
You
not.
can pass the horizontal test. You're still on that one.
Do we have a horizontal test?
Yes, you do. You don't know.
Alright. Let's quickly do this now. I want to see something. Oh, yeah. Just this part here. So if we have, okay, so inverse of parabola is not a function.
Mm.
So yeah. Oh, I must just do this. X positive or equals 0. Alright. Now we're gonna look at things like the domain and range.
No, but then isn't that other statement saying that we can limit the parabola?
We can
Limit the inverse function of a quadratic. The inverse of a quadratic.
Oh, okay. We can limit the domain of the parabola so that the inverse of the parabola is a function. Ooh. Oh, okay. Cool. Alright, so domain and range.
They used to limit the parabola.
Alright. If we limit the domain and range of the initial parabola, then we can have the domain and range. We can have the inverse of the parabola as a function. Okay, if we limit domain of parabola then inverse can be a function. Alright, so what we just did here, this is just mental gymnastics to see if we can plot stuff. So extra, but at least we learned something. However, if
that was just to prove a point that the inverse of a function is not
inverse of a
function.
inverse of a parabolic,
quadratic.
quadratic function is not a.
It's not a function.
All right. So this means if we simply consider the first quadrant of our axis system and our green graph h of x, we limit it like that, and there's our red line, then our inverse runs like that.
So we're limiting the domain, the x-axis
Values
greater than 0 or equal to 0.
So in other words,
that way the inverse doesn't have any negative
negatives, yes.
Okay.
So we must always have that x is positive or greater than, and we must also always have that x over 3 and x is positive or greater than 0. So if we limit that, definitely. But also, remember that minister who said, but also.
No.
I remember that. But also, if we have...
It sounds like something Angie would say.
Who?
Angie.
Your Minister of Basic Education. Our Minister of Basic Education.
Sounds like something she'd say.
I think a lot of civil servants speak like that.
Mm-hmm.
That's pretty much how many people speak, so it kind of makes sense that servants would speak the way everyone else speaks. Do you not agree? Are you in agreement? So if we also restrict the domain of our green function to be 0 or less, like that, then we can also have the other half of the inverse become a function. Because
in a way we're making it a linear.
Hmm?
In a way we're making it a linear function.
It's not exactly linear. I see what you're trying to get.
Exponential.
Oh, you mean like that?
Yeah, something like that.
I see what you're trying to get at.
But it's not that.
But it's not that, yeah. I see what you're trying to make the association. Look, associations are great if you want to remember stuff. Yeah. But the best way to get the full marks is always to apply the correct procedure for the context.
Yeah, I know. I'm saying it looks like one.
And yeah, it does. It does remind of that, definitely. No, X is not that. Yeah, not that. Ooh. Okay. This one, we must be careful. Be careful. We must be careful because it's only the negative half of that function. That is a function. And here, we must be careful as well because it's only the positive half of that is a function. So, in two cases where x is positive for the original function, then the positive of the inverse is a function and x is greater than or equal to 0. And for the part of the original function that is negative, then the negative half of the inverse function is a function. Okay, and this is interesting. So the domain of a function equals the range of its inverse. Let's write that down.
Yes, because you saw x and y. So
pretty much,
x
yeah.
becomes y and y becomes x. That's why the range and domain are pretty much the same.
Yes. Alright. I like that. So the domain of f is the range of the inverse, and the range of the function. English is escaping me. I wrote rain, then G. Range of f of x equals domain of f inverse of x. Alright. Similarly, a restriction on the domain of the function results in a restriction on the range of the inverse. And this applies also to restrictions as above. Alright. Then in this case, if we are to determine the range of h of x, It would simply be the domain is a set of x values such that x is an element of real numbers. What would the range be? Set of y values such that y is greater than or equal to 0 and it's an element of real numbers. I think I should also have the same x is positive thing. So it should be x is positive and x is also a real number. And I guess likewise here, domain would be set of x values such that x is positive and it's an element of real numbers. The range is also set of y values such that y is positive and an element of real numbers. I'm guessing here the domain would be slightly different. That would be x is such that
X is less than 0 or equal to 0.
And a real number. And
no one's going to see that.
Okay.
No one will be able to identify what is that you wrote over there, say.
But I'm speaking over the mic.
Yeah, it's the people want to see. Other people are visual learners.
Fair enough. I'll write visually significant text after using the eraser to erase that small looking stuff. Alright, so domain is set of x values such that x is negative and an element of real numbers. The range is set of y values such that y is positive, since we are squaring anyway, and an element of real numbers. For the orange function, domain would be x such that x is positive, right? And an element of real numbers, whereas the range is y less than 0, definitely, and an element of real numbers. Hey, and I guess the work we just did sort of covers everything for quadratic functions in as far as the worked examples go. We'll do homeworks maybe over the weekend. Hopefully we'll be joined by our other classmate and then we can sort of brush up and then do exponential functions. Yeah, we'll finish off here for today for maths. So we'll continue when is Saturday? It's 3 days from now, so 24th. Yes.